Okay. All right, so yesterday, the day before, we talked about limits, how to solve limits with graphs and tables. And that's great. And you might say, why is there any other way to mess with the limit? Why would I bother with any other way of solving limits? And the answer is that you can't graph everything. You might say, well, Desmos can. And I know there's more powerful things than that free internet graphing thing out there, and there are. But there are some things you can't graph because they are all algebraic terms, okay? If you have formulas that are like functions that are nothing but formulas, which is what happens a lot of times when we're dealing with the real world, we're dealing with medical or scientific or engineering situations, we don't have all those exact numbers. We're dealing with, like I said, like formulas and things like that. We might know some of the numbers, we might not know all of the numbers for the formula. And so what we want to do is we want to do some analysis. We want to figure out what the limits are. We want to figure out eventually something called the derivative and the integral. And in order to do those advanced things, we have to have the limits, but you can't find the limit if you don't have the graph. So I need to show you ways of finding limits without graphs. Okay, but we're gonna, like everything here, we're gonna start off with the basics. So I think I call this 2B, solving limits. I mean, the informal name would be solving limits without graphs, but the technical correct name is solving limits analytically. That's like what the textbooks are going to call it. And by analytically, we mean with analysis, and by that we mean with algebra. All right. So we're going to start off real nice by talking about the different types of functions that there can be. Okay. And then what we'll do is we'll see there's these types of functions, and there's these types of functions, and there's these types of functions, all right? And then we'll figure out how to use algebra for each one of those, okay? So sort of like break the problem down. So the very first type of function are functions that look like this. We'll just put like maybe a 1, 2, 3, 4, 5. That's 5. F of x equals 5. It's always 5. All right. Let's do a little bit of this will be kind of like a warm up for us. What is the limit of f of x as x approaches 3 of that particular function?
5.
She says 5. What do you say, Sarah? What do you think? What is the limit of that function as x approaches 3? As the x values get closer and closer to 3, what do the y values get closer and closer to? 5. Mitzi, would you agree with that? All right. Well, you're all pretty good there. What if the function looked like this? I'll use g of x. G of x is always -2. What is the limit of g of x as x approaches, I don't know, 1? So as the x values are getting closer and closer to 1, what are the y values getting closer and closer to? This is a very simple, straightforward answer. He says -2. Mitzi, would you agree with that statement? Yeah, because if we were to do a table, it would be like -2, -2, -2, -2. What about the other direction? -2, -2, -2. All right, it's pretty boring, right? But hey, we like these type of boring problems. They give us hope. So, in fact, these types of graphs are called, or these type of functions, these are called a constant function. and they take the form f of x equals c, where c is any number, positive, negative, decimal, whole, whatever. And for constant functions, the limit I'm going to change the letters on here, just allow me here. I'm going to call it B instead of C, all right, for reasons that you'll see here in a second. Well, I mean B because traditionally B is the y-intercept, and that's where these things are. Okay, so the limit of B as x approaches C, meaning as x approaches any particular number along the x-axis, of that is going to equal, see if we can apply the formula here. Kirsten?
I'm sorry.
You don't know what that's, you know what the answer's going to be here? Alright. The limit of 5 as x approaches 3 is 5. The limit of
Would it be B?
-2 is that which one's, yep. So the limit of B as x approaches C is B. Yeah. Maybe I wasn't making that as obvious there. All right. So there you go. That's one of our rules. That's the constant rule there of limits. But let's go ahead and graduate here a little bit up to something a little bit more complex. Still going to have straight lines, but they're going to be at an angle. Okay? So this is f of x equals 2x plus 3, and I'm interested at the point 1, x value of 1. So what is the limit of 2x plus 3 as x approaches 1? Now let's be honest here. Is there anything fancy going on with that line? Nothing really fancy. There's no gaps, there's no jumps, there's no breaks, there's no holes, there's no crazy oscillating, there's nothing, it's just a line, right? So as I'm getting closer and closer to 1 from this way, and closer and closer to 1 from that way, on this nice, well-behaved function, wouldn't it make sense to say that, you know, it's approaching whatever the function value happens to be, right? It's approaching, in this case, how would I figure out where that circle dot is? Anybody? Yeah, I could plug in 1 into that function. This is approaching 2 times 1 plus 3, so it's approaching 5. What about somewhere else? Maybe what about over here, like -10? The limit of 2x plus 3 as x approaches -10. Well, as we're going this way, we're approaching this particular point. And as we approach it from the left, it looks like we're just zeroing in on that point, which is the point on the graph. Okay? We're zeroing in on it. Okay? So it's just by way of explaining, it's not like those graphs last week or the other day where we saw something like that, you know, like weird stuff like that where you're approaching this way, you're approaching this value, and coming from the other way, you're hitting something else, you know what I mean? Or everything was nice, but there was a hole there, but then there was a, you know what I mean? There's nothing weird, there's no asymptotes. It's literally just approaching f of c, f of x, right? It's approaching that point right there. So in this case, we could say that's going to be 2 times -10 plus 3. So that's -20 plus 3, so -17. So would that be true of any, of any other point that I pick here? Like What about -1? Would you all say that the limit is also equal to that point right there? What about -20? Would you not say that the limit is equal to the point on the line? Okay, so it's really nice that with this line. Now, what if the line looked different? What if the line looked like that? Would there be much of a change? The question is, would the limit, if I said, what's the limit right here? What's the limit of this function as x is approaching -2? Would you not say, well, it's approaching the function value at -2? I think that's pretty reasonable to say. So, what we can do is there is a name for all these type of functions. They're called linear functions. And they all have the formula f of x equals mx plus b. We've known that for a long time. And what we've kind of observed is that the limit of mx plus b as x approaches c now let someone else other than Robert answer this. What did we do in both this situation and this situation? Kirsten?
We put it to the other side of the equal sign and put the number like the x, and we just answer it to find what it approaches, like.
Mm-hmm. All right. So you said let me see if I can. I think we're on track on like on this one. We took that one and we substituted it in. We plugged it in, right, for the x value on that expression, and then also with the -10, we plugged it in for the x value right there. Okay. So let's apply that right here. If it's the limit of mx plus b, so we're going to kind of think algebraically here as x approaches c. This right here is the generic form of this type of function. So so keep talking to me, Kirsten. What do you think I would put over here on this side?
M times c plus b.
Yeah, m times c plus b. So on nice, well-behaved functions like these, it looks like you can just substitute it in there, right? You just say, well, whatever c is, I'm going to plug it in to that one. Let's see if we can apply that very quickly. I'm going to give you a function, for an example here. The limit of 5x plus 8 as x approaches 2. All right? I don't need a graph to solve that problem. You don't need a graph to solve that problem, right? All we need is calculus knowledge. And calculus knowledge says, intramural altogether class, what type of a function is 5x plus b?
Linear function.
Linear function. How do you solve the limit of a linear function? Substitution. Plug it in. In fact, that's this. You could say that arguably that today's lesson is the substitution method for solving limit problems. Okay? So, Mitzi, substitute that in for me.
18.
Good job. All right. You might be like, Mr. Goddard, I thought calculus was going to be more difficult than this. So far, all you've had to do is have the ants go marching, tracing along the graph, and now just substitute it in. I've known how to substitute for a while. Am I right? Yeah. We could say, in fact, for both of these, I don't know if you want to write this down. So put another way, and you'll need to adjust the.
Yeah, I did.
The limit of any function b, well, hold on, I should probably put mx plus b. Here we go. The limit of f of x as x approaches c equals f of c.
Oh.
If f of x is a constant function or is a linear function. And that process is called just the direct substitution method. All right? I don't know about you, but I like the direct substitution method. I don't need to graph. I literally just plug it in. So now we have the question, I wonder if the direct substitution method works on any other types of functions, any other function families. Do y'all remember other function families? Quadratic, okay? So kind of moving up the polynomial food chain here. So quadratics, if you remember, when you graph them, look like parabolas. And I'll label it here. This is a quadratic function. They look like a U or an upside down U, a happy face or a sad face. Alright? Sad face when you first learn about quadratics because it seemed like a lot of work, but then they're happy face afterwards because you're like, they're not that much work. And they take the form f of x equals ax squared plus bx plus c. Now, I've got the problem where I've got c right there, so I might say, I'll say plus d. For example, something like f of x equals 5x squared plus 7x plus 9. That would be an example of a quadratic function. Now, Robert, does that quadratic function look pretty well behaved to you?
No.
So let's pick any particular c. I'll pick a c value right here. And as we travel along there, along that function, getting closer and closer to c, doesn't it kind of look like that it's approaching the actual function value? Just like it was with constant functions? Just like it was with linear functions? Yeah, it is. In fact, that is true. The limit of ax squared plus bx plus d as x approaches c is in fact a times c squared plus b times c plus d.
You said ax squared, right?
Yep, ax squared plus bx plus d. Like if that's the formula for the equation, for the function, then what we've determined is, yeah, the limit is exactly the function value there. Okay? Now I know this might be, it's kind of ironic because I spent the whole first lesson telling you that the limit is not necessarily the same as the function value. We were talking about the difference there, right? It was like the limit is like what we're getting closer and closer to, what's the trend, and the function is like what is the actual point. But the thing is that there's a lot of functions and a lot of places on those functions where the trend is what the actual point is, or what the way that she is at school and the way that she is at home is actually the way that she behaved on that particular day. Okay, so I would add quadratic functions to this list. I was linear with a really messed up thing because this thing's annoying, but whatever. So if it's a quadratic function, yep, just plug it in, substitution method. Does anyone, kicking back to maybe Algebra 2, remember any other function families? Robert?
Exponential.
Just go with the next natural one.
Exponential.
Linear, quadratic, remember what comes after quadratic?
The one with the cubic.
The cubic, yeah. We're gonna speed things up here a little bit here, ladies, because there's definitely a trend here. So a cubic, if you remember, would have ax cubed plus bx squared plus dx plus e. So anything that has a cube in it. And let's just look at that. Are there any breaks? Are there any jumps? Are there any gaps? Nope. In fact, I can pick this point and I can say, what is the function approaching from the left and from the right? And the answer is, it's approaching that function value. I can pick this point right here and I can say, what is the function approaching? What is its limit from the left and from the right? And the answer is, its function value. This is a nice, well-behaved function. And that is true of cubics. That is true of the next level, ax to the fourth plus bx cubed plus dx squared plus ex plus f. So anything that has an x to the fourth, anything that has, which is called a quartic, anything that has an x to the fifth, which is a quintic, sixth, seventh, eighth, all of those together, you can use the direct substitution. You don't need the graph, you just plug it in. So, quadratic, cubic, quartic, all of those actually are part of a larger family called polynomial functions. Polynomial functions take the form ax to the m plus bx to the m minus 1 plus, I'll go to d, dx to the m minus 2, all the way down to like the end, to just a single number here. So it could be 50x to the 20th plus 17x to the 9th plus, see what I'm saying? Like anything that's a polynomial that has pluses and minuses and the x is to a certain power, the direct substitution method will work. Okay? Would y'all like to do an example of this perhaps? I think we should. Example. What is the limit of the function 50 x squared plus 3x plus 2 as x approaches 4?
Whoa.
Do we have an undo? Sometimes we'll put parentheses around the equation. Ladies and gentlemen, this right here is a polynomial function. It's well behaved, it's continuous, which we'll have a definition for formally next week. But because of that, the direct substitution method will work. So we just will plug in 4 every time we see an x. So that's going to be 50 times 4 squared plus 3 times 4 plus 2. You're always welcome to grab one of these calculators when you walk in. Anybody have a calculation on that?
814.
Say again?
814.
Alright, polynomial functions, direct substitution method, it works. Just plug it in, substitute it in. Hooray. Alright, so now we'll deal with some other type of functions. I heard you mention exponential functions. Exponential functions look like this. F of x equals, normally it's a times b to the x, where x is the exponent, okay? Notice before, x was the base, and you had like numbers, like 2, like squared, third, fourth, something like that. So, this is now the x is the exponent. Exponential functions. So, an example here would be something like f of x equals 2 times 3 to the x. Notice that this is different from two x to the third. Sorry, do you see the difference? This is like what we were seeing a minute ago with the cubic, where x was the base and the numbers were the exponent. Now we've got x up here. But guess what? Are there any gaps there? Are there any holes? Are there any crazy jumps? Nope. It's pretty much a nice continuous function. It's smooth all the way around, right? So exponential functions, also good for direct substitution. Okay? What about logarithmic functions? F of x equals a log base b of x. For example, f of x equals 2 times log base 10 of x. Well, guess what? That's a real nice function. If I'm, marching along here, if I'm curious, what is the limit as I'm approaching this particular point from the left and from the right? The value that it's approaching is also equal to that function value. Okay? So, logarithmic functions, direct substitution works. The limit of 2 log base 10 of x as x approaches, 20 is, I don't need a calculator. Well, I might actually will probably do the log, but 2 log base 10 of 20. Just plug it in, and then plug that into the calculator.
So for that one, for the exponential function, it would be, if we were to do lim.
Yeah, I gave an example of the function. I didn't really give an actual example of the limit problem. So yeah, let's say that what is the limit of 2 times 3 to the x as x approaches 9 would be 2 times 3 to the 9.
Oh, wait. Oh.
Okay.
Are we feeling okay about all this?
Yeah.
Yeah, we're just plugging it in. I mean, I could tell you at the beginning of this lesson, you can plug, to solve the limit on polynomial, logarithmic, exponential functions, constant functions, all you do is substitute in and you're fine. And I can tell you that, and you'd be like, okay. And I can give you this homework and be like, look, we're just plugging it in, see? Look, we're just plugging it in, see? Look, see, this is how it is. You got it? We're good, right? But that wouldn't really get it in your mind about, what type of functions these are and what they look like, and that they are, in fact, nice, well-behaved functions. There are a few more functions. I think, what do you mean? Quadratic function. No, not quadratic. Square root functions. I don't know what color this is. Oh, it's red. I don't know why that's there. Fine.
Oh no.
Square root functions start off here and kind of go sideways. So this is something like, this is a square root function. Kind of looks like a logarithmic, but it's not quite logarithmic. So it's f of x equals the square root of a to the x. Normally it's like square root of a to the x to the n, but we'll just kind of do something like that. And guess what? No gaps, no jumps, no craziness, no asymptotes. If I was looking for what is the function approaching, what is the limit as we're approaching that particular point, it's literally the point on the graph. Square root functions, good to go for direct substitution. The limit of the square root of 10x as x approaches 5 is equal to the square root of 10 times 5. So that'd be square root of 50, which if you remember last year we broke that down, so that'd be square root of 2 times 25, so 5 root 2. We love the direct substitution method. For a lot of the trig functions, it also works, like sine, cosine, tangent. Trig functions. Same. So Robert, if you can stand up, that's fine. There's sine, there's cosine. Now tangent is kind of weird if you remember. Tangent kind of did like this little thing, and there was
Wow.
the asymptotes. So tangent, bad graph, has some asymptotes, so you can't do direct substitution. I mean, you can do direct substitution pretty much anywhere you want on tangent, except for at those asymptotes. Because of those asymptotes, it doesn't exist. Okay? But for most trig functions, direct substitution is the way to go to find the limit. So you don't always need to go to Desmos and do a graph and figure out where it's approaching and do the whole table. If you're able with your eyes and with your brain to be able to identify what type of function it is, then you can just do direct substitution and you'll be good to go. Alright? Believe it or not, that's pretty much the conclusion of this lesson. But we've got a little bit more than 5 minutes left. We got almost 6 or 7 minutes. So I'm going to give you this homework, and we're going to pick the hardest problem. Hold it. I did not tell you. There's one type where it doesn't work ever hardly.
Is it on the homework?
Yeah, it is.
Where's the one?
Sorry, I forgot the weird one. I forgot what the one that normally does have holes in graphs and things like that. Oh my gosh, how could I forget this?
Is that the step one?
Yeah, yeah, the stepwise, or that's step back. Okay, what's going on here? There are some graphs that look like this where they'll have holes and they'll have asymptotes sometimes. Okay? And they are formed from ratios of other functions, and they are called a rational function.
Is that the tangent?
No, tangent does look like that, but it repeats. This is one that literally just looks like that. So something where you have like P of x over Q of x, where P and Q are polynomials, okay? So, for example, f of x equals x plus 2 divided by x plus 3 and x plus 7. Anytime where you have like something divided by something else, okay? These guys right here, a -3 and a -7 are going, those are numbers which can cause that denominator to not exist. And anytime you have the denominator not exist, you're either going to have a whole or you're going to have an asymptote. Okay? So let's just look at that particular function over here. In all reality, this function is pretty well behaved. Okay? If I was trying to find the limit right here, no big deal. Because look, the limit is the function value right there. Or maybe this bar here. If I was trying to find the limit of that particular point, well, the trend is the actual dot. See what I'm saying? But there's a couple of spots on the rational functions where it doesn't really behave very well. And I kind of made those indications on this one. What is one of those spots that it doesn't behave very well?
Gap. Oh.
The gap? Or that?
Oh, the asymptote.
Yeah, the asymptote, and also that hole. Okay? So as long as you're not trying to find the limit of that spot or of this spot, you're good to do just direct substitution. Okay? If you have a gap or if you have an asymptote, then you're going to have to use advanced algebraic techniques, which is tomorrow's lesson.
No.
So, but
Okay,
there's one
click
on
in
here,
here.
right?
What's that?
There's
Isn't
one
there
on
one
here.
on here?
No, I mean, there's rational functions on there. Look at that. Do you see any rational functions? Do you see anything where there's something divided by something else?
Yes.
Which one?
Oh, and 7.
Number 8 and 7.
Number 8 and number 7, okay?
It's
Well,
close.
what's that? You don't need to skip it. You have to ask yourself, is Mr. Goddard asking us to evaluate that limit at the annoying spot, at the spot where it misbehaves? Okay? Well, you'll just have to plug it in to find out. If you plug it in and you get a 0 in the denominator, then you're out of luck. Okay? Because because you don't know how to solve it. But I'll tell you right now, if you plug in -1 into number 8, you're not going to get 0 in the denominator. If you plug in 2, look at it. You'll plug in 2 on number 7 in the denominator. What are you going to get? 2 squared plus 2.
Yeah.
Yeah. Are you going to get 0 in the denominator?
Mm-mm.
So you're safe. You just plug in the number, and what I'm asking you on those two are something like this point, or something like this point, or something like this point to evaluate, where it's well behaved. In fact, rational functions, I mean, they kind of get a bad rap. They're like, oh, rational functions, they don't work everywhere. You can't do direct substitution everywhere. Yeah, you can't do it 2 times. Everywhere else you can do just direct substitution. In fact, direct substitution is awesome. Like 99 problems out of 100 when it comes to limits, direct substitution is the way to go. right? But there are some times that direct substitution is not going to work, and you're not going to have a graph, and that's what tomorrow's lesson is about, okay? How to figure out what we're getting closer to. What are we getting closer to if we don't have a graph and we don't have, you know, a really nice, well-behaved function. All right. How are you feeling looking at these 10 problems? Good? Can someone remind me how to, what am I going to do with secant if there's not a secant button on my calculator?
Second.
Secant is also equal to 1 over cosine. Okay? Also, in calculus, we don't use no stinking degrees. It's all radians from here on out, boys and girls. Alright? So if you're using a calculator, make sure it's in radian mode. If you have questions about that, I'll be happy to answer them. Today we talked about evaluating limits analytically. Basic.
You're not afraid.
Like and subscribe. See you next time.
Wait, now you're afraid.